My name is Ali Kujuri. For those of you who do not know me, it's a pleasure to have you all in this lecture number, Engineering Science lecture number 6 for this academic year, and also the 153rd lecture in the series since we started in 2006. On behalf of the Engineering Science Department and the School of Science and Technology, let me thank you all for attending this lecture. I would like also to thank Mr. Sharon Marivani and also Kate Lab, who are helping me in this in organizing this lecture series. Well, as you know, generally at 5:30, you know, the delicious pizza arrives, and then you can help yourself, of course. Now, the next talk will be on February the 6th next year. The title of talk is How Machine Sees the World. And it is done by Dr. Kilman Zeng, who comes from Arkansas Technical University from Roseville, Arkansas. Our guest speaker for today is Mr. Roger Nichols, and the title of his talk is 5G Mobile Wireless, a 5G Overview and a Market Update. Mr. Roger Nichols is the 5G Program Manager from Keysight Technologies. His 35 years of experience in the wireless test and measurement industry spans various roles in manufacturing and research and development, and crosses the evolution from analog cellular radio through LTE and now 5G. He has spent 8 years as a director of marketing for Keysight's mobile broadband operation, responsible for delivering the wireless test sets and systems used in all major design and certification labs, as well as manufacturing facilities worldwide. I would like to say that Mr. Nichols, in fact, this is in fact his third time. We are really thankful to him, because as the 5G development, goes on, we really need to have the updates. All right. So that's why, in fact, he's here, and I'm really thankful that he accepts our invitation, as the 5G technology is really very important for all of us, especially that soon when you are going to go to work to start, this 5G can be a very good area for you to work. So also that not only that, I usually invite him because you can see that he's really an excellent lecturer. Okay, so let's just applaud him.
Thank you, Ali. Has anybody in this room seen me speak before? You have?
Yeah.
Right. All right. I'll try not to bore everybody. So I started as the 5G program manager at Keysight Technologies back in March of 2014. So it will be 6 years this upcoming March that I've been working on this. And it's been fun to watch it progress from what was at the time mostly applied research to now some new nascent commercial systems that have been deployed in a few places around the world. So we're going to start with a quiz rather than ending with a quiz. And the first question is, how many times has the phonetic alphabet been invented in the history of the world? Does anybody know? Phonetic alphabet, right? That's the alphabet where a symbol means a sound, right? You're going to...
every time there's a new language spoken.
It turns out only once. The phonetic alphabet was developed, we are fairly certain, in Egypt a little bit more than 5,000, or a little bit less than 5,000 years ago, and every phonetic alphabet that exists is derived from this, if not directly, at least conceptually. So that's a pretty interesting concept. How many times has the printing press been developed in the history of the world? There's an answer of 1 there. It's a good try. It's done twice, right? 15th century in Europe, but 300 years earlier in China, they developed movable type. So I bring this question up mostly because we are in the middle of a similar revolution. When the printing press was invented, particularly in Europe, that had a massive change on how easy it was to communicate things, how much less expensive it was to communicate things. And in some ways that was good, but it did lead to about 300 years of hostile religious warfare. So it's not always a good thing, and our invention of the internet has its pros and cons as well. So how many generations of mobile wireless communication are there?
5.
Well, 4. We started with analog voice, moved to digitizing the voice, moved to being able to have mobile data in the 3rd generation, and then all packet data in the 4th generation. But that is correct, there are 5, because we actually have 5th generation services available now. So what will it be? There's a lot of hype associated with this. The items on the left of this slide were part of a vision that was put together by a research project back in 2013, 2014 in Europe. And I have always appreciated the way this is captured, because it really is, from a user's perspective, from a business perspective, amazingly fast, really good service in a crowd. That's not always the case with today's cellular systems. The experience follows you around, very fast, real-time and reliable communications, and lots of things talking to each other and communicating. But with that vision comes a lot of hype. Wireless gigabit, anywhere, anytime. I was raised in Simla, Colorado. Does anybody know where Simla, Colorado is? Me neither. They're not going to have wireless gigabit in Simla, Colorado. Tactile wireless, internet, remote surgery, right? Low latency, high reliability. Does anyone want to be operated on by a doctor who is actually maybe 100 miles away through the hands of a robot? Maybe not. 1,000 by 1,000 MIMO. I've seen this claim. If you know anything about MIMO, you know this is actually pretty tough. Driverless cars, a lot of hype around that. Probably be about 4 or 5 decades before we have real driverless cars in any kind of great perspective. 100 bits per second per hertz. Spectral efficiency, that's a claim, right? Does anybody know what the state of the art is right now in cellular system? 1 bits per second per hertz. That was the 4th generation. Do you know how much better that is than 3rd generation? None. And they're all between 1 and 2 bits per second per hertz. So getting to 100 is going to be tough. And this is my favorite, 1 trillion connected devices by 2025. So let's talk a little bit about that. The road to 1 trillion devices. This is a headline from the ARM conference 2 years ago, 2017. In a short, quick 20 years, we're likely to see 1 trillion connected devices. Whenever people toss around big numbers, you got to take a hard look, because there may be some issues with this. So I did a little bit of math on this. Now right now, does anybody know what the number of connected devices there are in the world? It's somewhere between 5 and 10 billion. So the difference between 1 billion and 1 trillion isn't that much, right? So 1 trillion seconds is 31,000 years. Folks, this is a big number. 1 billion, it's a big number, right? So it's 1,000 billion. So if we made that many devices, it would take us 20 years at a rate of 1,600 per second to have in the world 1 trillion devices. So for reference, there are about 100 mobile phones manufactured every second on the planet today. So that's a big number, right? And not everything is going to be a mobile phone. There'll be little devices and the Fitbits and the other things you're going to have on your person, or other sensors or detectors. But at 1,600 a second, you get to 1 trillion if none of them fail, and if they're all still working after 20 years. So let's see, there's just in front of everybody, about every other person's got a cell phone sitting in front of them. How many of you are going to be using that same device in 20 years? Right? Nobody's raising their hand. So the number is actually a lot bigger, and if you do it's a great piece of decreasing term math that you can do on this, and the number that you have to manufacture is a lot bigger than 1,600 a second. Let's look at it from another perspective. If you just look at the signaling that 1 trillion devices would generate around the world, and signaling is the term we use for the interchange between a client like your mobile phone or a pager or whatever, and the base station, that is the negotiation to set up a communication link upon which you would then send the payload data, the data that really matters, the cat video or the tweet or whatever. So just the overhead, the signaling overhead, if we said every device averaged about 10 bits per second. Now some people think that's a little bit high because a lot of these devices would have very low signaling rates. But a number of these devices would have very high signaling rates simply because they might be automated vehicles where you're going to have a lot more signaling going on because of mobility and other issues. If we had a trillion devices running, that means that at 10 bits per second, just the signaling would be 3 exabytes per month. That's 10 to the 18th. And the total data used, mobile data, in Q4 of 2017 was about 13.5 exabytes per month. So I'm pretty sure we're not going to have 1 trillion connected devices in 20 years. I consider that to be bull, but 5G really is happening. So there's a lot of hype out there, there's a lot of mythology. Do your homework and find out. So I'll talk a little bit about cellular communications. We'll talk about what's going on in 5G, what's driving the demand for this new generation, what are some of the technologies, and what does the timing look like, and then what's the status of the rollout, who's involved, what are the applications, and then a couple of conclusions. So, cellular communications. Most of us have mobile phones. Anybody in this room not have a mobile phone? If you don't have one, you're probably afraid to admit it. So number one, simultaneous talk and listen. At least the appearance of a simultaneous uplink and downlink. That means that every device in a cellular system has to have a transmitter and a receiver that are operating in close concert with each other. That means it's a fairly complicated system to manage interference or other issues. Spatial frequency reuse. This is how we have done most of the spectral efficiency improvements over the last 150 years, which is by making the cells smaller. And the cell means I'm using a certain set of channels right here, and a couple miles away they're using the same channels, and they don't interfere with each other because of the way the system is designed. So reuse of spectrum is a big deal because spectrum is expensive and it's precious and a lot of it's used up, particularly if you try and go through the FM radio dial. Then there's mobility, mobile wireless. So mobility turns out to be very difficult. It's not just mobility in terms of overcoming Doppler shift and group delay, so the bits don't land up on top of each other and you end up with fading problems, but also how do you manage handovers, moving from one cell to another? How do you manage billing? And when I carry my device to Japan, it works just fine. They seem to figure out how to send me a bill. It's a lot of complex things go into mobility. And this is actually very interesting because something like 85% of all mobile phone calls and communications are initiated and terminated indoors these days. And yet, we have very sophisticated technology so that we can drive and watch cat videos at the same time. The other issue is the communications channel itself. So back when I first started using cell phones, it was an analog system and it was a circuit switch system, in which case that means that for me to talk to you, there's a dedicated communications channel, and even if we're not exchanging information, that channel is dedicated to the two of us. So if you're having an argument with your significant other and you're talking to them on the phone and you're giving each other the silent treatment, that channel is dedicated to you, even though there's no information going through that channel. And we've moved now to a packet switch system, which is how LANs work, another networking system, in which case the channel is open between you and me when we're communicating only when information is flowing. And that means that when information is not flowing between the two of us, the network will hand that channel over to another client and server or pair of clients to interchange information. It's a more efficient way to use network resources and available communication channels. And this is one of my favorite quotes from Misha Doler at King's College London, which is, Intel, Cisco, and Microsoft don't get together every 10 years and invent a new internet. And my response to that is, but 3GPP does. And 3GPP is the third generation partnership program. It is a large standards body. It's an industry consortium. You pay to be a member, and then they have meetings quite often, 6 times a year, depending on which subgroup you're in, and they develop the standard for the communication. How do these devices interact? What are they going to say to each other? How do things work so that the devices are going to work the same way everywhere in the world? There is a 3GPP meeting for radio access network and system aspects, both happening in Reno right now as we speak. I was there over the last couple of days, and I just drove from Reno this morning, and it's kind of a remarkable process. There's 3,000 or 4,000 people there broken up into meeting rooms and talking about the most intricate, ridiculous details you have ever seen in your life. And they're all arguing because if I'm Ericsson and you're Nokia, we may argue about a particular part of the standard because I might have intellectual property that makes this part of the standard easier for me to do than you. And those kind of battles exist all the time. We try to stay technical, but politics and business needs all come together. Second page of the primer is that the cadence of this market is very fast. It's very frantic. There's a lot of money at stake. There's a lot of people involved, a lot of different companies. It's all governed by not just standards, but also policy. And everybody is in it to make a buck because we all want to eat and we want to buy more phones so we can watch better cat videos. The other thing is the big companies, they fall hard. Back in 2006, Nokia was the #1 cell phone manufacturer in the world by far. They were the #1 smartphone company in the world by far. Nobody in the US had a Nokia smartphone. It didn't matter. Everybody outside the US did. But BlackBerry was the smartphone company. That was the Wunderkind. That was the great thing to have back in 2006. Apple was not in the cell phone market in 2006. And now they dominate almost all of the profit in that business. And then the wireless modems, these magical chips that are inside of your device that manage the link between your device and the base station. There's a number of companies listed up there. Only one of them is still in the business since back then in 2006. The rest of them have sold out or exited the business or sold themselves. In fact, Infineon has been sold twice. Infineon was purchased by Intel, and then Intel just took their modem business and sold the whole thing to Apple. So it's a tough business to be in. The competition is pretty fierce. You have to innovate very quickly to stay on top of it. And I like to say that late, no matter how good, always fails in this market. There's a lot of times when you can be a technology follower and be successful. But in this market, it's exceptionally difficult to do so. And that's particularly true for my company where we make electronic test equipment for not just this industry, but others. So it's a kind of a frantic market. So what's this all about? From the first generation to the fourth generation, we've had a lot of successes. We moved from just being able to carry your phone around and have a voice conversation with somebody to moving data around in a really high-speed way with applications that we really could not have dreamed of 30 years ago when I started using a mobile phone. We've gone to where you can carry your office anywhere, and really it's all about information management. It's not just communications. And that's a big change for how we all use these systems, but there are limits. Who here in the room is happy with the reliability and the speed of their mobile device, of the speed of the connection? There's always a couple people that raise their hands. They're lying. Watch out for these people. They have integrity problems. It is a reliability issue. There are limits to reliability and speed and latency of the system, and it is a energy-hungry system. And I'll describe a little bit more about that later. What that does is build constraints. The application space is pretty much exclusive to entertainment. You might shake your heads and say, no, that's not really true. Something around 50 to 60% of all of the mobile traffic right now is video, right? And most of that is people like me watching YouTube videos on how to play the saxophone and the guitar better. Okay, so it's entertainment. Bear with me here. But what that does is it limits the network operator's business model, and they really want to expand how they approach things and get business from entities that are not traditional users of the mobile wireless system. So we're working on how do we expand that process. Now there are some people that believe this is not needed. I know this gentleman, William Webb, and this is something he published back in 2016, so it's been a while, but he was quoted with very much this same skepticism just a few weeks ago in The Economist magazine, published in Britain. And he says, hey, the data growth, the use of data is going to slow down, and this stuff is too expensive anyway, and we can fill the gaps that exist to accommodate where things are going in this market with existing technologies. And to add to that, LTE 4G has a ways to go. Of the almost 8 billion subscriptions that exist in the world today, less than half of them are fulfilled by 4G. So a couple of key things you pick up from that graph on the right side there. And number one is there's more subscriptions in the world than there are people. So how many in this world, or in this room, have more than one mobile subscription? Nobody's raising their hand. Does anybody have Amazon Kindle? There's a couple of hands that went up. Does anybody have a car that has a link to the mobile network? So there are many people that have more than one subscription and actually don't know it for mobile cellular. So it has a ways to go. But then let's take a look at the demand that's going on. So number one, the use of data is exploding. This is growing between 40 and 60% per year. And right now, the data consumption, this is mobile data consumption, not your Wi-Fi on your computer, but this is your mobile phone and like hotspots and that kind of thing, 29 exabytes per month. So an exabyte is 10 to the 18th, a billion. So how big is 29 exabytes? It's a number that I can't comprehend. I was just telling you, hey, here's a guy up here tossing around big numbers. Is this guy full of baloney or not? Well, there's my source, Ericsson's Mobility Report, June of 2019. This is a fascinating thing in the public domain. They update it about twice a year. It's worth a read every time it comes out. So to illustrate this, it's about 450 million 64 gigabyte hard drives that get filled up every month. And if you line those little things up, that's a picture I took of one of my thumb when I was on an airplane flight making this slide. It's 11.3 million meters. That's the distance from here to Hong Kong. Or if you go the other direction, the distance from here to Tel Aviv. So line up all those thumb drives. Every month, that's how much data is thrown around over the air using mobile devices. And it's growing. There's also a lot of energy being used, about 1 kilowatt hour per gigabyte. Now that number's gone down. It used to be about 2 kilowatt hours per gigabyte. But we've got more gigabytes now. It's not a green system. 14 terawatt hours is what China Mobile used in their mobile system in 2012. And they had about 1.1 million base stations. I figure that power cost them about $1 billion that year. So a power bill is $1 billion. It is the number one operational expense for a mobile operator, more than salaries, more than depreciation. And it's hard to manage because there are 3 million off-grid base stations around the world, meaning they have to be powered by a generator. Powering these with solar is not practical yet. This technology is just not there yet to power mobile sites with solar. And there's about 7 million bad grid base stations. A bad grid is a grid that goes down at least 8 hours out of any day. India consumes 2 billion liters of diesel fuel a year to power their cellular systems. So this is not a green technology. And peak connection densities are going up. I don't know, has anybody here been to Japan? A couple of folks. Have you ever been to Japan? There's a train station in Tokyo called Shinjuku, and about 7 million people go through Shinjuku every day, and every one of them is looking at their phone. And let me tell you, the cellular service there is excellent. It always works because the Japanese customers are extremely demanding. And the connection densities are really high. It's very, very difficult to manage a mobile system with connection densities that high, and they're going to ask for even higher data rates. And then there's latency. LTE, best case, end-to-end latency is 20 milliseconds. They're talking about latency in 5G of about a 1 millisecond end-to-end, meaning I do something on my device and the server or the client on the other end can see what happened 1 millisecond later. So that has there are some physical limitations to this. Light is only going to go 186 miles in 1 millisecond, and that is in free space. If you put that on fiber, it slows it down by, it's only about 60% of the speed. So that is going to be a challenge to get super low latency in these systems. But the lower latency environment is what is going to drive new businesses to utilize this capability. So what are the technical things that are being done? So first, a quick primer of what a network looks like. You've probably seen these before. The phone, the user equipment, is part of the network. Make no mistake. There's a radio access network. In the case of LTE, it is the evolved Universal Terrestrial Radio Access Network. That's the base stations and the interconnects between those. And then there's a packet core, and that's the router. For all practical purposes, that is what routes the information as it comes in through from the rest of the world to where it needs to go. The packet core also keeps track of things like billing, and as people move around in the network, there's a mobility manager, that kind of thing. So these all have new names in 5G. The RAN is called the 5G RAN. There's a very innovative name. And then the core is the next generation core. So I'll talk a little bit about the technology changes that are going on in this space. First, we're going to talk about what it appears like from a user perspective. This is my very sophisticated picture and diagram of a cellular network. There are 3 macro cells. There's a bunch of people using the system. It's working okay. It's not really well connected to Wi-Fi, usually through competing gateways, and you kind of have to think about whether or not you're on Wi-Fi or whether you're on cellular. It's getting better, but it's a little clunky. And if you're in a crowd, it doesn't work very well. Does anybody go to big football games, baseball games maybe? Can you use your phone very well in those games? Sometimes yes, most of the time not. I even find when you land on an airplane, on a wide-body airplane, everybody turns on their phone, checks Facebook, the system just comes down. So service in a crowd is tough. These connection densities are very difficult to manage. And as I said before, the total system consumes somewhere around 2% of all of the power generated on the planet. The networks themselves about 0.5%, and then everything else, charging batteries, the manufacturing process and the supply chain, all of that consumes the rest. So it's expensive. So what is 5G going to do? Number one, better service in a crowd, and most of that is going to be accomplished through more cell sites. And in this case, I've just illustrated that by making sure that where there are crowds that are going to gather, there's a bunch of cell sites there that have been added, and they're mounted on light posts. Much lower power, decreases the overall energy in the system, and but you end up with much better coverage, and the crowd is now better covered. Now, there are other things that are being done to improve the connection density situation, but this is what will make the biggest difference. The next is amazingly fast and reliable communications. And I just illustrated this by putting in millimeter wave antennas with directed beams at the people that are paying for that kind of a service. So when you get up into the millimeter wave space, the 24 to 52 gigahertz territory, which is what is being defined right now for 5G, then the widest bandwidths that are available to users tend to be in upwards of 800 megahertz, which allows you to, it's just a bigger data pipe. You can just send more information around. But what's not in the picture is what I also talked about, which are many things that are being done to decrease the latency and to increase the reliability of the system. And that's being done on the air interface, that's being done in the network design. There's a number of changes being done so that the way that the information arrives to you is a lot faster and in a much more real-time basis. And then all things communicating. So the change in the picture here is a little complicated, and we'll focus on the gentleman talking while he's driving in his car. Does anybody do that in this room? Nobody's raising their hand. Yeah, good. Oh, okay, there's the honest guy, right? That person in the car is probably endangering the gentleman that's talking on the street right next to the car. And notice that the person on the street right next to the car is getting his downlink relayed to him from either a nomadic base station that's sitting on top of the car, or potentially that is actually what's called a vehicular user equipment, or a VUE, and it's a device-to-device communication, and the downlink is then being relayed from the macro cell that's nearby. And the uplink is being relayed to a neighboring cell through somebody else's phone, also using device-to-device communication. This does not happen in today's systems. There's a very small piece of device-to-device that's enabled in LTE. It doesn't do very much, but this is where things are headed for 5G to facilitate a better communication situation. There's a lot of scenarios where that would work out. And to have the uplink come from one cell site and the downlink, the uplink go to one cell site and the downlink come from a different one, that also doesn't happen in today's systems. That means a much more complex system. Also, what's not in this are, you'll notice that the gentleman in the car, his downlink is coming from a nearby light post rather than from his own base station. And his uplink is then going to the macro cell that is nearby. And the car is probably an automated vehicle, or at least is getting some information from the network about its environs. In fact, maybe even information about the gentleman standing next to the car, because his device is communicating with the car and saying, hey, I'm here, don't run over me. And so that's a real application that's being developed right now. And that means that maybe the car is somewhat autonomous and is not endangering the life of the individual standing next door. The other thing that's not in this, there's two things I'll talk about. One of them is, I've talked about uplink and downlink going to different cell sites. So another way to do things is have one cell site manage all of the control of the device, all the signaling, and another cell site manage all of the payload data. So maybe one cell site has got a lot of very fast switching capability and it can manage a bunch of different phone calls. Picture a bus full of people using their phone driving through a cell, and as soon as it goes into another cell, the cellular system has to do a handover for everybody in that bus as quick as possible. It's a pretty difficult thing to do. Well, there may be a cell site that's designed to manage that really well, and a different cell site handles all the data because it has just a big fat data pipe and it can handle a lot more data. That might be another way to design things. That is also called user plane, control plane splitting, and that doesn't happen in today's cellular network. So that's a new thing for 5G as well. And then this doesn't also have the picture in it of all the other things that are communicating, like sensors, parking spaces, people's Fitbits and watches, and all the other things that are talking at the same time. In order to accommodate lots more data, a lot more interchange of information, control information from one cell site to another, and lower latency, we have to have a faster and more reliable wired network that holds this all together. So the typically fiber optic, sometimes radio interconnect systems on the backhaul from the network, from the antennas, has got to be a lot faster with lower latency. The core is becoming virtualized, so it becomes, the functions in the core become virtualized functions that are running on standard CPUs rather than dedicated, expensive hardware that's inflexible. And that enables a software-defined network that could, for example, turn the power off of these cell sites where those people are, where the crowd is, once the crowd dissipates. Because if you don't need the cell sites there, then why constantly broadcast energy in that space, which consumes most of the power in a cellular system? The power amplifiers on cell sites are about 70–75% of all the power consumed in a cellular network. And then you have a much more seamless connection with maybe private networks, in-building Wi-Fi, in-building cellular, that kind of thing. So that's the intent of where we're headed with 5G. So from a technology standpoint, I'll just do a quick summary of a few different technical areas. Spectrum, the air interface, a little touch on millimeter wave and MIMO, and then virtualization of the networks. This is a quick picture of the spectrum situation. Notice that the scale on the top is logarithmic, and that the lowest frequencies that are defined by 3GPP are actually about 450 megahertz. It's not used very much for cellular because the antennas have to get too big to be practical. So a lot of this starts around 600. So T-Mobile has a big 600 megahertz piece of spectrum that they bought a few years ago, and they've been deploying 4G and now more recently 5G in that space. There's what I don't have in here is existing bands in the 7 to 8 to 900 megahertz area, the 1700 megahertz area, the 1500 megahertz area, the 1900 and 1800 megahertz area. What I've put in here are some of the new bands. So 2.5 and 2.6 in this area, Sprint has moved their WiMAX spectrum over to use this area, and I think China Mobile is at 2.6 gigahertz. 3.5 is a new band that's been opened up in many places, a little bit in the United States with this thing called CBRS, but the licensing situation is very problematic with CBRS, so it'll be a while before 5G is deployed in any kind of large scale there. The territory between 4 and 5 gigahertz in China, maybe in the USA. There's a lot of arguments on the FCC about that right now. And definitely in Japan. And then the millimeter wave spectrum, the 28 gigahertz space is now up and running in the US. The 39 gigahertz space in the US is up and running. They are going to auction 47 gigahertz next month. And they just finished auctions of 2.4 and then 24 gigahertz area and 25 gigahertz area in the United States a few months ago. They haven't opened up anything in Europe yet. Those auctions are coming. China will do their thing probably quite a bit later. They tend to drag their feet on these a little bit. And then Japan and South Korea have opened up the millimeter wave space as well. So lots of new spectrum made available. And this is really just to be able to handle more information, whether that's the lower frequencies, 3.5 to 4.5 and 5 gigahertz, or then the millimeter wave space up higher. In order to have a new generation of cellular communication, you've got to design a new air interface. Whether or not that's mandatory, I don't know, but certainly 3GPP likes to do a new air interface design to accommodate any number of a zillion things. Generally, it's about getting better spectral efficiency, being able to take advantage of wider bandwidths, hopefully making things more efficient from an energy standpoint, dealing with higher mobility. 5G is supposed to work up to 500 kilometers per hour, so about 320 miles an hour for high-speed trains. You think about the Doppler problems of two trains coming at each other going 300 miles an hour each. It takes a little bit more to design a system that will handle that. Lower latency, and there are changes to every one of the facets of the air interface, whether that's what they're doing for modulation, how the waveform is designed, all the numerology for orthogonal multiplexing, multiple access schemes, new forward error correction channel coding schemes for the data, and also changing the frame structure. People ask about frame structure, what's that all about? Well, frame structure is if you're sending packets of information from me to you, I send you a packet of information, you have to tell me whether or not you got it and whether or not it was accurate. And that implies latency, right? Because I have to wait for you to tell me whether or not you got that thing. Well, now they're designing things like self-contained frames. So within that same frame, I get the acknowledgement that the packet was received. So I don't have to wait for several frames later before I get that information. There's a lot of detail in here. There's a great public webcast that Keysight has created that is a description of the yet another new air interface in 5G new radio. You can find that on the websites. Get a hold of me, I can point that out to you. It's about 2 hours long, there's a lot of details. We'll talk about millimeter wave just a little bit. So these high frequencies are pretty hard. You have to design the radio frequency integrated circuits with different materials because you're up at very high frequencies. The wavelengths are much shorter, hence the term millimeter wave. And the other issue is that there's a larger propagation loss if everything else is the same. If you consider a 0 dB antenna gain, 28 gigahertz has about 20 dB more loss than 2.8 gigahertz, or 1.8 gigahertz, sorry. And you have to make up for that because link budget is the way that I get a signal to you, and that by the time it gets to you, the signal to noise ratio is high enough to where you can figure out what I'm saying. And if I'm going to lose a factor of 100 more at this higher frequency, I have to figure out how to overcome that. So I get antennas that have gain. Well, antennas have gain because I focus the energy in one direction. That's how that works. And there's one way to do that. We could put a fixed gain horn antenna. I had a little fun here and taped that to my cell phone just for the sake of illustration. And that's really great, but then you have to point it at the cell site so that the signal to noise ratio is high enough. And so how do you accommodate this? We're not going to put gimbaled fixed gain horn antennas on our devices to do this sort of thing. What will happen is phased array antennas or other ways to focus the energy in the right direction. You can't quite see it in this picture, but there's an 8x8 phased array patch antenna on each of the compass points on this. It was a proof of concept that Intel did a few years ago. That would sit in one of those shark fin things on the top of your car as a vehicular user equipment, VUE. And that was a pretty cool proof of concept. It works, and it will electrically steer the beam where it needs to go to have it pointing at either the receiver or the transmitter so you can maintain the radio link and do that appropriately. Now there's a lot of people that will say it will never work. Well, it's working now. Right now the standard is such that this is really only feasible with a fixed wireless system, and that's how Verizon and AT&T have opened up their initial commercial enterprise for millimeter wave in some cities, and it's a fixed wireless system. So it's a replacement for wireless broadband to your home, for example, or wired broadband to your home. And they don't have to put a wire between where they are and where your house is, which I would like because the broadband in my house really stinks. I get ADSL, so I'm about 5 megabits per second with my home internet. My cell phone is much faster. Unfortunately, it's more expensive. So it is happening now, and that is going to work, and it will continue to get more work. The standard right now is being hashed out to deal with mobility. And that has to do with things like beam correspondence. Can I make sure that I can steer my beam to where the base station is? And what is the signaling that goes on between the two entities so that that beam can be steered correctly? There's a huge amount of work in this space. in the standards body right now. Most of that will be complete as of release 16, which will be finished in March, I think. So that's pretty cool. So you see a lot of antennas, individual antennas. They're little square patch antennas. A lot of times when people see lots of antennas, they think, oh, that's MIMO, right? This is not MIMO. So those of you who've had the classes understand a little bit about what MIMO is, multiple in, multiple out. If you think about sending a radio signal from me to you, there's a line of sight path, but there's also a path that would bounce off of a wall, for example, or a mountain or whatever, and that path has a different distance, and the bits that go in the line of sight will arrive to you at a different time than the bits that get to you on the same frequency through a different channel, which is a reflected channel. That's a problem. That's called multipath fading. Well, MIMO takes advantage of that, and will send different bits down the reflected path than it will down the direct path. It's pretty cool. It involves an awful lot of signal processing. It doesn't always work really very well, but they're making progress on this. In 5G, they're taking that to the next phase and creating something called massive MIMO. So it means the number of base station antennas is a lot more than the number of user equipment that's being served. And the graphics are not accurate, and the math is way over my head. So I'll describe a little bit about how massive MIMO is intended to work. This is a simulation. It isn't practically speaking how it's actually implemented, but it's a good way to simulate what's happening. In this case, I have an array of antennas. There are 50 in this case, and they're all monopole vertical antennas. And it's a linear array of antennas. So it will actually transmit and receive exactly the same pattern this way as it does that way. So ignore this back here. We're just looking at the stuff going from left to right. There are 4 users. You can't quite see, but they're here, and there are 2 up there. And there's a intended user, that's a solid red dot, and they're the victim users. Those are the open red dots. And the way this works is that everybody's signal, every user's signal is on every one of those antennas with a different gain and phase relationship, which allows the energy for any particular user, since it's all superimposed, to be where it ought to be. So in this case, the target UE is in a nice bright spot, and the victim UEs are in dark blue areas. They actually are not getting any of the target UE's energy, and hence their signal-to-noise ratio and their signal-to-noise interference ratio is great. In the case here of looking at UE number 2, it is in a light spot, sort of. It's at the edge of a light spot. And the victim UE right next to it is in a node, so hence it won't have any of UE2's energy. The same for UE3. When they get close together, this is tough to manage, but I've actually seen actual demonstrations of this where you can put them pretty close together. It works pretty well. And of course, the 4th user equipment down there in a nice bright beam with the other ones not getting any. So that is what massive MIMO is all about, and it enables you to decrease the amount of power that you have, the total power you have coming out of your cell site, because you can focus the energy a little bit more. Right now, the cell sites put kind of a flat amount of power out in, like in a sub 120 degree sub cell, and whether or not you're in it, that energy is still there and being used up. This is a little bit more efficient. It also enables you to use the same resources, the same time and frequency resources for different users in the same cell. So theoretically, can drive a much higher use rate. Now Sprint has about 10,000 massive MIMO base stations installed right now. They featured this at the Super Bowl this last year, and they actually had pretty good coverage, pretty good success with it. The other thing to keep in mind is that the user equipment are sending pilot signals on the uplink constantly. so that the base station can figure out what the channel actually looks like, because the pilot signals get distorted. The base station knows what they're supposed to look like. The pilot signals get distorted. It creates an inverse of the matrix and does pre-coding on all the antennas, so that as the UEs move around and where they are with respect to the channel changes, then the base station can make up for that on a real-time basis. That's also the subject of about a 90-minute webcast if you're interested in knowing more about that. The other thing that 5G is going to do is force new technology inside the device. When you create a new air interface, a lot of what enables that are things like new innovations in technology, Moore's Law, where you can cram in more signal processing inside the device. And the demand for speed, of course, is on that air interface. And the target for 5G is a peak theoretical speed is about 10 gigabits per second. Well, the theoretical speed is never going to be accomplished, right? So you're always going to struggle with that a little bit. But inside the device, there's a lot of bits moving around really fast. There's a lot of things you have to do to make this work so you don't use up too much battery power. For example, if you have a 4K display, ultimately it's a bitmap display, and that's 9 gigabits per second that has to move from some signal processor to the display. That's a lot of bits. Inter-chip, moving information between the chips, between memory and processors, interfaces with HDMI, the serial interfaces that go outside of the device, or Bluetooth, and then things like, the state-of-the-arts, the states of the art. And this is a little old. This is improved a little bit, but a serial connect in copper. From a practical standpoint, you can get about 10 gigabits per second out of a single serial connection in copper at about 10 picojoules per bit. That ends up being a lot. Deep in the lab, they're getting sub-picojoule per bit on these connections, but using up energy for these is a major deal, because who's happy about the battery life on their cell phone? Same guys raising their hand. Don't believe them. And as an example, the Wi-Fi system in your computer, if I'm manufacturing one of these computers and I'm going to buy a Wi-Fi chip from the guys that make Wi-Fi chips, if you use more than a watt in the entire system, the radio, all the digital signal processing, everything like that, I can't use it. So the budgets are really, really tight, and all of this fancy speed and latency is going to drive a lot more magic deep inside the devices for electronics as well. What happens in the network? It's virtualization. So this is a model of the LTE Evolved Packet Core. MME is a mobility management unit. There's serving gateways to the radio access networks. There's a packet gateway to the rest of the world out that way. The home subscriber server, that kind of thing. Every one of those and all the routing of the information in the old days was done with dedicated high-speed hardware, which is great. It's got great performance. It has really good energy efficiency, but it's very inflexible. It does one thing. And so ideally, if we have really, really fast general purpose processors and we can create the functions of the network as software entities, then they can be a lot more flexible. And that's where things are moving. AT&T claimed they had virtualized their packet core back in 2016. And about 2 months later, I was talking to a guy at AT&T, and he shook his head and said, yeah, we actually run it in parallel with our old-fashioned core because it's not fast enough. We're still trying to figure out how to get the architecture right. So this is going to take some time, but they will get there. Not only in the core, but also in the radio access network. They're virtualizing the RAN, which makes it even more flexible as well. So in a conventional situation, if you think about the protocol stack that operates on a base station, and this is a basic model. You've got RF at the bottom, a physical layer, a MAC, media access control, and then radio resource management, and then higher up to the network management. For a traditional system, excuse me, all of that functionality is in dedicated hardware, an ASIC, in some cases FPGAs, but people don't like those because they cost a lot of money and they use a lot of power. It's in an ASIC in the base station. Well, what if we could virtualize some of that and move more of that to be centrally executed as a software entity that could communicate with a high enough bandwidth to maybe something was just a radio at the other end. And this is actually also really happening right now, and it enables you to be much more flexible with the network. Maybe even change it on a real-time basis as to where you are in the stack. And this enables a number of issues, a number of great ideas. These are terms that don't mean too much, but picture the ability to change how much functionality any base station has, or more importantly, in Europe, and I think in Korea, they already have laws in some cities in Europe where different network operators not only have to use the same antenna mast, which happens here, you see groups of cellular antennas on a mast, and those are generally different companies. Sometimes it's just different bands. They've then moved in Europe to where the different operators use the same antenna, the same radome, which ends up being a super complicated antenna system inside the radome. And now they're moving to where the operators have to use the same base station. So exactly the same hardware. Well, how are you going to do that if you don't have some of that cell site base station protocol stack in a software situation? So you've got two different software entities, one for Vodafone, one for Orange, and they're both actually operating in exactly the same situation. It means less cell sites out there, which is easier for everybody because cell site placement is expensive and frustrating for everybody involved. So the state of the art is about halfway through the MAC layer, and actually it's come down a little bit based on what I learned at a seminar I was at recently, just a few weeks ago. Of course, there is a state of physics that you can't overcome. They will not virtualize the antenna. I haven't seen any technology yet that will accomplish that. I leave that as an exercise for the student to develop the next virtual antenna. You'll make billions of dollars. So what's the status of the deployment? So first of all, let's talk about how the network operates. There's components that get built by all these companies, and they are then sold to the people that make devices and network equipment, like base stations and then the networks themselves. They sell to the mobile network operators, who also sometimes sell services to virtual mobile network operators like Cricket and that kind of thing. Cricket doesn't have a real network. They just buy time on somebody else's network and resell that to you. That makes, that's a kind of a win-win because they can sell time that isn't used. That then, you get over-the-top applications. That's what OTT means. So Facebook is one, but there are other things you pay for, like Hulu and other things like that, which are applications that don't have anything to do with access, but that's where actually the real money is, by the way, in cellular. This is why AT&T bought Time Warner, because that's where the content is. And finally, it's us. And we are the ones that we give money to the operators and the OTT folks. And the money, everything operates in a policy and a standards framework, and the flow of money then goes back through the system. And what I like as a test equipment provider is that just about every part of this has to do some kind of test. And so that's where we come in, and it's been kind of fun to be part of this for 5G. I'm running out of time, but I'm pretty close here, so bear with me a little bit. A lot of this started back in about 2010, and then the industry got pretty serious in 2015 with some initial framework discussions, some showcase at the Olympics in 2018, the Winter Olympics in South Korea, and then the first networks were up and running in the US at the end of 2018. And then a number of announcements in 2019 for cellular systems that have gone up and running on 5G, various places around the world. And what else was I going to say? And then we'll see a lot more happening in 2020. It takes time. Here's another quiz. What's wrong with this picture? This is a screenshot from my phone back in April. Does anybody see something wrong with this picture? There's actually two things.
You haven't turned off your YouTube notification?
Up in the upper corner, that's a good question. it says 5GE, right? So this is hype. This is AT&T's, that's their 5G evolution. What this is an advanced form of 4G that they've deployed, and now it comes up and says 5GE on your device. You folks, AT&T people have probably seen this. It started in San Francisco, and it's started to move further north these days. The other thing that's wrong with this picture is the battery's full. So this is just a quick snapshot. These slides will be available, by the way, because there's nothing in here that's super confidential. Of all the people, kind of the leaders that are involved and the frequencies that are going on, and approximately when they are going live or have gone live. So all the 3 major operators in China went live with their 5G systems on the 1st of October. All 3 major operators in South Korea did that last March, about halfway through the month. Korea claims to have 2 million 5G subscribers right now. It's a country of about 50 million people, so they're moving fairly fast. But it takes time. And you can see with the some of the dates there that this gets turned on and then rolled out slowly because it costs a lot of money. And if you wanted evidence that there are people other than Facebook and cat video users that are looking long and hard about how to take advantage of the new capabilities in 5G, this is a sample of a number of headlines. Again, some of this is hype, but this is real work going on in the industry around the world, and that's a sample of headlines I've collected over the last 6 months or so in various vertical application spaces for 5G. Industrial IoT, that's automating factories using wireless rather than wires, interconnecting things wireless, which turns out to be extremely difficult because inside of metal buildings is a pretty hostile radio environment. Transportation, all kinds of stuff for transportation. Clearly entertainment, this is where most of the money is going to be for the next few years. Absolutely, entertainment and advertising, make no mistake. Finance industry, which is a Luddite in mobile technology. I mean, it just introduced mobile banking within the last year and a half or so, and it's coming. They're going to take full advantage of the capabilities of 5G, and true to form, they have a lot of money. Farming, and then obviously things going on in the medical space. So, last situation. Here's a history quiz for everybody to keep you entertained. Does anybody know when the first telegraph was developed?
1850?
1850? 1792. Claude Chappe. This is, I don't know if I say his name properly because I don't know if he has an accent on it. This was used in France. Napoleon loved this. It's a semaphore-based system. So it's not electric, it's visual. Tower has some weird complex flags on it that you can see a couple miles away at the next tower, and the information is relayed really fast compared to horse. There's a great story about the first network security problem in the book The Count of Monte Cristo, using this very system. It's my favorite novel of all time. I recommend you read it, Alexandre Dumas. So the question you thought I was asking is the first electrical telegraph. And I heard 1850s. It's just a little before that. It was invented about the same time in the US and the UK, whether that was Cook and Wheatstone or our friend Samuel Morse. The first radio telegraph, developed by an Italian guy in the UK, 50, 60 years later, 1897. And the cell site at that time was about 1/6 of the planet. All right, if you think about it, right? What happened on the 25th of June in 1876? Anybody know? Is anybody there? I heard telephone?
Telephone bill.
It was Custer's Last Stand.
Oh, okay.
Where the 7th Cavalry of the U.S. met its maker at the hands of a much larger Sioux and Cheyenne force. But you are correct. On that very same day is when Alexander Graham Bell demonstrated the telephone at the Philadelphia Centennial Exposition. One of those is an example of good communication. One was an example of bad communication. I will let you decide which. So it's been quite a while since we started with the telephone, and now we're carrying them around in our pockets. So spread spectrum, you might have learned a little bit about this, is hopping the frequency around or spreading it out a lot with lots of wideband digital modulation. Bluetooth uses spread spectrum. A lot of things use spread spectrum. We'll probably be putting frequency hopping in cellular at some point. Who invented this? I know he knows.
Yeah, I know.
When was it invented? It was invented during World War II by the most beautiful woman in the world, or that's how she was advertised, Hedy Lamarr. There's a biography written by Richard Rhodes of this woman, and it is fantastic. And she's a truly amazing individual. She was a very famous actress, obviously, but a super mind. And she actually was effectively came to the U.S. on asylum because she left her husband, who was an Austrian man, turned out to be a little too close to the Nazi forces. She wasn't very happy about that. She left, took off, and came to the U.S. She invented the concept of spread spectrum and gave it to the U.S. Navy during the war, obviously as part of the war effort, so they could potentially use it for secure communications between ships and torpedoes. They looked at it for a while and said, it'll never work, right? How many of you use Bluetooth today? Right? You bet it works. So did we need these? Cell phones, text messaging, cameras, cat videos, GPS, compass, infrared, all that kind of stuff. Did we actually need this? And I just suggest maybe we just define the word need, because this started as a luxury. And now, does anybody lose their power over the last month, ever? How many of you lost your power? How good was the cell service when your power went out? Some places it was okay, other places it's pretty bad, right? That's because the cell sites don't have, they have battery backup by law, but how long do the batteries last? Like 2 hours. So they don't have backups in that. So did you find yourself wanting your phone to work when you didn't have power? Of course. So it has become something we rely on, just like Alexander Graham Bell's telephone has become something we rely on, as opposed to people looking at it and thinking, why would I ever want one of those things? So that's it. I apologize, I've gone over just a few minutes. And I don't know if the pizza's here or not. If it's getting cold, then I'm really in trouble. I'll take a couple of questions, and I'll stick around for other conversations as well.
I noticed you had a bubble of 47 to 60 gigahertz. Is anything really serious going on at that upper frequency?
So the U.S. will auction the 47 gigahertz band next month.
Okay.
So there's a 1 gigahertz band that they will auction between, I think it's 47 to 48, or it's just below 47 to just below 48, I can't remember. Is anything going on there? Not yet.
Not yet.
Are people going to put money into that? Probably. It becomes, 28, a lot of these new systems, they actually use silicon in their power amplifiers,
Yeah.
even though it has single-digit energy efficiency. But it's kind of working. It's a lot harder to do that at 47.
Right.
So it'll be expensive, but I think they'll use it. The 60, so 57 to 71 is unlicensed now, and there is work going on there with some things. I have a wireless HDMI at home, for example, that's at 60 gigahertz.
Okay.
And then there's a lot of backhaul that is implemented in the 71 to 76, 81 to 86 paired spectrum. That's pretty common. And they found ways to make that fairly inexpensive. Usually it's a gallium arsenide. So that's used. And then 3GPP is doing a study on bands above 52.6 right now.
Okay. Thank you.
I saw that you had for the industrial IoT.
Yep.
You had something there. What are the other considerations for the, shall we say, the IoT implementation? Let's say in a big land and so on, you want to
Yeah.
control coming on a,
So for industrial IoT, the the intent is to be able to reconfigure your factory without moving wires around, right? So there's a bunch of different ways to do it. So interference is a problem, typically inside of a big metal building. There's lots of issues. Reliability is a very important thing because now the connection has to work. And so you have to have reliability in place. Latency is a super big issue to make sure that that works well also. So typically industrial IoT will be a private network. That's probably how it's going to work. Germany has already set aside a 100 megahertz band exclusively for industrial IoT. The idea of having private networks that use 5G technology is pretty common, and I think that will be leveraged to manage that. And it's going to take some time for it to take off. This is early work because even the standard for the low latency, high reliability is relatively new. So they're still working on some of the issues there.
Okay, thank you. Any questions? All right, yes, please.
I've got a couple of questions, but both of which relate to that the proposed network traffic managing scheme that you mentioned early on in the presentation, whereby like there's a different path for the uplink and the downlink.
Mm-hmm.
Could you comment a little bit on like what some of the drawbacks of that management scheme might be, and also is the development of that technique, is that dependent upon the use of the higher frequencies that are associated with 5G, or is that just a kind of general development that's happening in parallel with the new protocol being developed?
So to the first question, the reason why you might do uplink and downlink to different cells, it actually, the heuristics of which cell you're associated with today are based exclusively on signal to noise ratio, maybe not so much on power consumption. So it actually might be a lower power consumption if you would do a connection to both sites like that. As crazy as that may sound, because you might be a lot closer to one than another one. The problem with doing that, the drawbacks, or what you have to get to work, is that now you've got a coordination that has to happen between the two cell sites, where timing has to be pretty good. I mean, there has to be, very microsecond or sub-microsecond level timing accuracy, just to make sure that these two links happen at the right time, particularly if your application requires a tight link. The other drawback is that interference is harder to manage. If your uplink or downlink could be coming from anywhere, there's a lot of interference management algorithms in today's 4G systems that are based on the assumption that I'm associated with only one cell site. So the interference management becomes a bigger challenge. It actually might improve the interference in the system, because most of these systems are not noise limited, they're interference limited. But that's another drawback that could come from this. It does not rely and is not predicated on the addition of the millimeter wave bands or the other high bands. It's more about finding ways of separating either user plane and control plane, or making it a better way to manage the radio links depending on what you're doing. In the case I described here, it's actually a side link that moves you over there, because you actually may have a better link through your friend to that cell site than you do to the one that you're closer to, as long as that person is your friend, because your data is going through their device. So there's more security issues, and that becomes another one of the issues, is managing security.
Great, thank you.
Yep.
Okay, I would like to thank Mr. Roger Nichols for his excellent, really, I mean,
Thank you.
It's an excellent lecture. It was very instructive to have it for all of us, and let's give him applause, all right?
Thank you.